Hello everyone, my name is Rohit Singhal and we were discussing about the hydrocarbons. In the previous classes, I have discussed about the alkynes. I have started with the synthetic procedures of alkynes. I have discussed about its physical properties, and in these lectures we will discuss about the chemical properties of alkynes. So, chemical properties of alkynes. First, acidic nature of alkynes. I have briefly discussed about the acidic nature of alkyne in the previous lecture, where I have studied the introduction of alkynes, that alkynes are do acidic, that the proton, that what happens, why these two are acidic, and this alkenes or alkanes, these are not acidic. Why is this so? I have already discussed that this carbon is sp hybridized, these carbons are sp2, this is sp3. So, what happens is percentage S character in alkynes is more, that is around that is 50%. So, there is 50% as percentage S character. So, due to what happens that the electronegativity of the carbon increases, and if the electronegativity of carbon is high, that means it will pull up therefore, it will tend to withdraw the electron density towards it. So, what happens in that, it's abstracting the electron density of the CH bond towards itself. So, what will happen, the CH bond will become weak, and if the CH bond will become, that means the molecule is acidic, and it can easily cleave off the hydrogen. That means the CH bond weakens and behaves acidic in nature, but it is a weak acid, it is not a strong acid, not like H2SO4 or HCl, it is a weak acid. That means, if we need to abstract this hydrogen, we need a strong base. That means, to do this or to cleave CH, it means to cleave alkyne hydrogen, a strong base is needed. For example, if I react acetylene with sodamide, this is a strong base we have used in the synthesis of alkynes, it will form a salt and will release the hydrogen gas. Stoichiometrically balancing it, it will be half of the equivalent. So, sodamide is a strong base, it can cleave of the hydrogen. So, that is, and now we know why this alkynes behaves acidic in nature. Okay. So, but do remember the this hydrogen that is attached to the triple bond carbon, the hydrogen attached to the triple bond carbon is acidic. Only that hydrogen is acidic. Okay. For example, what I am trying to say is, let us say there is a case, there is there is propine. So, what happens if I react it with sodamide? That means what I am trying to say, that this proton is acidic, this proton will be abstracted, not this one proton. This proton is not acidic, this proton is acidic. This proton is not acidic, this proton is acidic, that is directly attached to the triple bond carbon, because that carbon is sp hybridized. Why it is? This carbon is sp hybridized, this carbon is normal sp3 hybridized. So, it is a normal alkane types of part, although its electronegativity a bit higher than that of normal alkane, because there is a C triple bond C besides it, but it will not be that much that the sodamide can abstract this proton. Only that proton will be abstracted which is attached to the triple bonded carbon, or we can say sp hybridized carbon. So, it will release NH3 gas, it will not release NH2, it will release NH3, ammonia will be released. If I react with the sodium, sodium is also a base, then it will form So, yeah, that is it. Moving on to the second property of it, that is addition reaction. If you remember, we have discussed these addition reactions in the alkenes also, and I have told the reason why these alkenes show addition reaction, because alkene is a electron rich center, rich center they have. Similarly, alkynes also have 2 pi bonds, they also have high electron density. That means they are they can give these addition reactions easily. So, as alkenes, like alkenes, alkynes also undergo addition reactions due to its electron rich behavior. 2 pi bond presence. These are also, alkynes are also electronically rich, that is why they tend to give the addition reaction, as we have seen in the alkene. So, similar reactions that we have studied in the alkenes follows in alkynes also. So, starting with it, let us take an example. We have studied the addition of H2 alkyl halides, halogens, this we have studied, right. So, what I am trying to say, let us take something, an example of H and Z, and what this Z can be, this Z can be X, this Z can be H, this Z can be OH, something like that. So, in general the reactions of alkenes, I am saying that C triple bond C H R dash here. This R or R dash can be hydrogens or the alkyl group CH3 CH2 CH3 kind of this, and addition of HZ. This HZ can be, this Z can be H X, so that means hydrogen can be added, HX can be added, water can be added, kind of this. So, what will happen? First of all, what will happen? A cation will be formed. That this is a vinyl cation, and reaction of this, now a Z minus will be remaining, and the reaction further with the Z minus will give up this moiety. So, in general I have discussed about this, specifications we will discuss in the upcoming reactions, but this is the general thing that what happen if if there is something like HCl or H2 or there is something H2O, means there is H part connected to something electronegative part or something like that. So, what will happen that H will cleave and will react first and it will form a cation, that is called vinylic cation will be formed, and this reaction depends on the stability of, if you have remember about these reactions, I have discussed that the stability of carbocation, that is an intermediate, decides the reaction, that how fast will the reaction, whether reaction will take place or not of vinyl carbocation. Okay. So, this is an intermediate in this, intermediate in such kind of reactions. So, the vinyl cation stability directly in we can say see the reaction stability in what way the reaction will go. So, the reaction directly depends on the stability of vinylic cation. So, specifically dealing with this, let us say addition of hydrogen, that is hydrogenation reaction. Okay. Nothing similar as we have seen in alkenes. What will happen? We will be needing some catalyst first of all, H2 nickel or palladium, whatever we want. See, one H will go there, one H will go there and will form R dash. Okay. It is formed an alkene. If the reaction will continue, means the hydrogen is added in excess, the alkene can further undergo the addition reaction and it will give the alkanes. Okay. So, this is the reaction of addition of hydrogen, that is hydrogenation reaction. Similarly, addition of halogens, that means X2 is added. What will happen? First of all, one molecule will be, let us say Br2 is added. Okay. So, this form. So, alkene bromide is formed, and again further reaction if the bromine is excess, the alkene can also undergo similar kind of reaction. That means, further a bromine molecule can be added and it will give okay. Okay. If you remember this thing that I have already discussed, the addition of bromine or the halogenation reaction in the previous case, that this is a test of unsaturation. So, here is also bromine, this is reddish orange in color and it will form colorless. So, test of unsaturation, and if you remember that this we have discussed in alkenes also. So, do remember while you are studying the properties of alkynes, the alkynes properties are not too dissimilar with the alkenes, almost similar. So, read them parallelly so that you will better understand that what these both are doing things. Nothing but this alkynes will first convert it, alkynes will first convert into alkene substituent and then it will further do the further reaction and will form the alkanes or alkyl halides or something related to the alkanes. Okay. Moving on to the next property. In alkenes we have studied this addition of water. Water can be added and we need some of the catalyst. Okay. Directly they do not react with water. If you want directly react with water, they do not react. As we have seen with the alkenes, they do not directly react with the water, we need some acidic media into that. Similarly, while with the alkynes we need some acidic media, H plus we need, or some Hg2 plus, that means mercury 2 plus ion we need. What it will form? On one side there will on one side hydrogen will be go, on hydrogen will go, and other side OH, and further reacting now. Okay. Now what will happen? You must be thinking that as similar, what will happen, an H2O molecule will be added and it will form or something like this. So it doesn't happen. What happens is, instead of adding another water molecule, a unique form, a unique something process happens with this alkene. What will happen? The process is known as isomerization. It's same that isomerization that you have discussed a bit about earlier, also you have studied in the earlier classes. What will happen? This is an enol form. This is an alkene, right? This is an alkene that starts with the ene, and this is alcohol, that means ol. Ene and ol, that means an alkene and alcohol present simultaneously. So what happens is, this convert into another form. What will happen? That this double bond will be transported here. It's actually not like this. That means a ketone forms, okay, and this is known as keto. So this is known as the keto-enol tautomerization. Okay, let's discuss slightly in a better way this. Okay, this is CH, this is OH. Okay, so it doesn't react with the H2O molecule another. What happens is, it undergoes tautomerization. Okay, what it undergoes? Tautomerization, or we can say isomerization. Let's first say it isomerization. What happens is, this hydrogen goes over there, and this okay, what is happening here? This oxygen is giving its lone pair towards the carbon. So what happens is, a double bond forming here. This double bond is shifting towards this carbon. That means a negative anion will be formed here. A negative, and this negative will take up this proton to form this one. This is ketone, or known as keto, and this is called as enol. Why this is enol? There is alkene and alcohol. This is a combination of okay, and this isomerization, and what happens is, this form is more stable. Okay, these exists these two forms, keto and enol, exist in equilibrium. However, what happens is that keto form is more stable. This is more stable. Okay, why is more stable? That you will study in the later classes. Why? So this keto form is more stable. That's why I've shown this arrow more. This arrow towards ketone form is the bigger one as compared to the arrow towards the enol form. So this is how we show the equilibrium error. The both sides are similarly equal. This means this more favorable. Similarly, this is more favorable. That means whichever the arrow is bigger, whichever direction the arrow is bigger, that moiety is more stable. Okay. So this is the keto-enol isomerization, and in which the keto form is more stable, and this exists in equilibrium. This is also known as, this kind of isomerization specific, there is a specific name to this kind of isomerization, that is called as tautomerization. So, that means these are keto-enol tautomerization is happening. Okay. So, this is a special kind of isomerization that is named as tautomerization. Okay. So, you now we have discussed a few properties, there are few properties left that we will discuss in the upcoming lectures. So, thank you.